Welcome to our video on analyzing stresses in structural components. This topic is a crucial part of any introductory course on the strength of materials in a mechanical engineering degree program. Whether you're a student or just curious about the mechanics behind engineering, this video has you covered. Let's get started.
Learning outcomes of this presentation. After going through this presentation, you will be able to
1. Define stress at a point in a structural component. 2. Explain how the stresses on a plane are determined and the stresses on two mutually perpendicular planes are known. And 3. Determine the principal stresses, and how the planes of principal stresses are determined. At a point on a surface, we can define three stress components. Firstly, the stress sigma E said, acting normal to the plane. This plan is identified as E said plane. Secondly, and thirdly, the stresses τ x and τ y acting on the surface in mutually perpendicular directions x and y. As these stresses are acting on the surface, they are called as shear stresses. Similarly, we can denote the stresses on the other two planes as illustrated here.
Stress transformation.
Stress transformation refers to the process of determining the stress components acting on a plane that is oriented at a different angle from the original coordinate system. This concept is crucial in the field of mechanics of materials, as it allows for the analysis of stresses on various planes within a material under load, helping engineers and scientists understand the material's behavior under different conditions.
Now we will consider a case of two-dimensional stress transformation.
When the coordinate system is rotated counterclockwise by an angle theta, each plane associated with the stress point also rotates by the same angle. The new coordinate system is x dash, y dash. The normal stresses on newly positioned planes are given as sigma x dash and sigma y dash. The corresponding shear stresses also take different values as shown. Our aim is to derive equations to find out the stresses on new planes sigma x dash, sigma y dash, and τ x dash y dash, in terms of the stresses associated with x, y coordinates, and the angle of rotation, theta. We consider an elemental area delta, A, normal to the x-axis, which forms an angle theta with the original x-axis. The forces on the other surfaces can then be written as shown in the figure. By considering the static equilibrium of the stress element, we can derive the equations for stresses relative to the x-y coordinate system, as presented here. By using these equations, you can find stresses on any plane, if you know the stresses on two mutually perpendicular planes.
Certain angles that satisfy these equations will correspond to maximum and minimum values of these stresses.
One way to determine the extrema of a function is to differentiate it with respect to the variable of interest and set the resulting equation equal to 0. So, we see how to determine these maximum and minimum values. By substituting the angles for the maximum and minimum stresses in the normal stress equations, we can obtain the maximum and minimum stresses. Also, by differentiating the shear stress equation, we can obtain the maximum value for shear stress.
Now, let's examine a graphical representation of the stresses on various planes. It is possible to demonstrate that the normal stress and shear stress on different planes passing through the point under consideration trace a circle on a coordinate system of normal stress and shear stress. This circle is called as Mohr's stress circle.
Let's look at again the transformation equations. We eliminate the angle theta by squaring both sides of each equation and adding the two equations together. Finally, we get the equation sigma x dash minus sigma average squared plus τ x dash y dash squared equals sigma x minus sigma y divided by 2 squared plus τ x y squared. If we take the right-hand side of the equation as r squared, then this equation resembles an equation for a circle, with radius being r, and the center at sigma average, 0.
This circle is usually referred to as Mohr's circle, after the German civil engineer Otto Mohr, 1835 to 1918. He developed the graphical technique for drawing the circle in 1882.
Next, let's explore the construction of Mohr's stress circle. Imagine an element with planes aligned along the x and y directions, labeled as A and B. Also, consider a plane C inclined by theta to the plane A. To construct Mohr's stress circle, it is necessary to follow a specific sign convention. In this convention, the normal stress is considered positive if it is tensile, and the shear stress is deemed positive if it causes a clockwise rotation of the element. We now look at how to draw the Mohr's stress circle for the stress element shown here. Using Mohr's stress circle, we can determine the points of maximum and minimum normal stresses, as well as the maximum shear stress. The point, P, indicates the maximum normal stress, known as the major principal stress, while the point, Q, indicates the minimum normal stress, referred to as the minor principal stress.
Also, from the stress circle, you can obtain the maximum shear stress values. Here, points R and S represent the maximum shear stress values.
From Mohr's stress circle, it is also possible to determine the orientation of the planes, relative to a known plane, that carry specific stresses.
By examining the physical stress element and the corresponding Mohr's stress circle, you can observe that the angle between two planes is represented as twice the angle between the relevant radii associated with the stresses on the stress circle. You can easily see that the angle between the two planes A and B is 90 degrees. The angle between the two radii corresponding to the stress points A and B on the stress circle is 180 degrees, that is twice the angle between two planes.
If we consider the plane C that makes an angle theta with the plane A, the point C on the stress circle can be located by rotating the radius GA in the counterclockwise direction, that is same direction of rotation of the stress element.
We will now look at an example.
The state of plane stress at a point is represented by the stress element below. Draw the Mohr's circle, determine the principal stresses and the maximum shear stresses, and draw the corresponding stress elements.
First, identify the stress points A and B on the normal stress-shear stress coordinates. Given that the A and B planes are perpendicular to each other, the line connecting points A and B represents a diameter of the stress circle. Next, find the center of the circle, point C, by determining where the line AB intersects with the normal stress axis. The points D and E on the normal stress axis represent the principal stresses. Now, calculate the diameter of the circle, using the coordinates of the 2 points A and B. Then the radius of the circle is 69.64. Then the length GC equals CF equals half of the length GF. That is 50 plus 80 divided by 2. This is equal to 65.
The length FD is equal to CD, that is the radius, minus CF. Then the length FD is calculated as 4.64.
Therefore, the major principal stress is equal to OD, which is equal to OF plus FD, that is 50 plus 4.64. Then the major principal stress is calculated as 54.64 megapascal. The angle, theta, between the radii CB and CD can be calculated. tan theta is equal to FB divided by CF. That is 25 divided by 65. Then this angle is calculated as 21 degrees. This means the position of the plane carrying the major principal stress is located at an angle of 11.5 degrees to the plane B. The minor principal stress is given by the length, OE. This can be written as OG plus GE. The length EG is equal to CE minus CG. The CE is the radius, which we have found as 69.64. CG has also already been found as 65. Therefore, EG is equal to 69.64 minus 65. That is 4.64. Therefore, the minor principal stress is 80 plus 4.64, that is equal to 84.64 megapascal compressive. Since the angle between the two radii corresponding to principal stresses located at points D and E on the circle is 180 degrees, the angle between the planes of principal stresses should be 90 degrees, that is normal to each other.
Let's now see the maximum shear stress. By observing the stress circle, you can see that the maximum shear stresses occur at points H and point I. The value is equal to the radius of the circle. That is 69.64 megapascal.
The position of the maximum shear stress plane can be determined in relation to one of the principal stress planes. Since the angle on the stress circle corresponding to planes of maximum shear and one of the principal stresses is 90 degrees, the plane of maximum shear occurs at 45 degrees to the principal stress planes.